Welcome. In this video, we're going to be solving the first Ethernaut challenge called Fallback. So let's jump right in. We can see here the criteria to beat the level is we have to first claim ownership of the contract and then reduce its balance to 0. Some things that might help are knowing how to send Ether when interacting with an ABI. So in other words, what that's saying is we have to know how to call a payable function that is defined within the contract and therefore would be included in the contract's ABI. Then also knowing how to send Ether outside of the ABI. So that means knowing how to send Ether just to the contract without calling any specific function. And then, even though it says Ether, this really could be any native token depending what chain you're on. So I'm going to be using Polygon, so this is going to be Polygon in my case. But moving on, knowing how to convert between Wei and Ether units, and then also the concept of fallback methods. And of course, knowing the concept of fallback methods perhaps might be the most important thing to first understand. So let's go ahead and look at that first. So you can see here in this solidity by example, fallback is defined as a special function that is executed either when a function that does not exist is called, or when Ether is sent directly to a contract but received does not exist, or message.data is not empty. So let's try and break this down even further here. So the first thing to understand would be there's actually two variations of fallback functions. The first one is actually called fallback, and the other one is called receive. So fallback can be either payable or non-payable. This payable modifier here is actually optional. So when you send Ether to a contract but receive does not exist, and fallback is not payable, then of course the transaction would still fail. But if fallback is payable, then that's when fallback would handle that transaction, or that instance when you're sending Ether to the contract. Also, the other criteria is that message.data has to be empty in order for this fallback method to be executed. So if you're trying to call a function and you're specifying which function that is and perhaps sending some parameters, perhaps not, that's again when fallback would come into play here. So that's usually the case when you're calling a proxy contract. You're basically trying to call a contract that exists on some other contract, some implementation contract for the proxy, and that gets forwarded to the implementation. So that's another topic for another video. But all we need to understand now, the next thing would be is basically that receive is the one we're going to be dealing with in the Ethernaut challenge, and that gets triggered when you're sending Ether to a contract and there's no message.data. In other words, you're not specifying a function, nor are you sending any parameters. You're sending empty call data to the contract, and you're only sending just Ether. And it could be, like I said earlier, it could be just any native token to that chain. So in any case, let's go back to the Ethernaut code here and see how we can hack this contract. So we can already see at the very bottom here, receive is defined in this contract, but let's actually go from the top here, one thing at a time. So as for the state variables, we have two public variables. First one is contributions mapping, so it's mapping the contributor address to the value that's been contributed from them so far. And you also have a state variable for the owner. So when the contract is constructed, the address constructing the contract will automatically become the owner. And then also that address will automatically get 1,000 Ether in the contributions mapping. Then we have this modifier only owner. So basically it performs this check. If the caller is not the owner, the transaction is going to revert. So if we fast forward a little bit down to withdrawal, we can see that's where the modifier is being used. So only the owner can withdraw Ether from the contract. Next, we have the contribute method. So in order to add a contribution and have it be recorded in that contributions mapping, you would need to call this function. And we can see here it's payable, so we can definitely send a native token to this function. And as was mentioned up here in things that might help, interacting with the ABI, so that's what it's referring to here, is knowing how to interact with the ABI, in other words, call a function defined within the contract that's payable. So we have this condition, though. We can only send less than 0.001 Ether. And then a couple lines below, we see that in order to become the owner, the contributions of the message sender have to be greater than the owner. And we already know the owner has 1,000 Ether. So becoming owner this way is not very feasible. It would take a long time, plus it would cost a lot of gas. So there's probably some other way to take control of the contract other than just by sending such small amounts of Ether over and over again. So if we scroll down even further, we'll see the receive function. And this is where the things that might help was mentioning that it would be good to know how to send Ether outside the ABI. So that's what we're doing here. This receive function is basically a way to send a native token to a contract that wouldn't require having access to these functions up here that are defined within the API. So in any case, we can see here that there's two conditions required in order to call this contract without having it revert. First condition is the value being sent to the contract has to be greater than 0. The second one is the caller has to have already made a contribution previously. So in other words, the caller would have had to have called this contribute method at some point previous to calling or sending Ether to the contract. And then once those two conditions are met, the message.sender will become the new owner. So I think the plan of attack should be pretty clear now. First, we will go ahead and invoke this contribute method so that our wallet address is added to the contributions mapping. At that point, we can go ahead and just send some native token to the contract. Then at that point, we will become the owner, and we can withdraw all the funds from the contract back to our own wallet. So let's go ahead and get started with that. Actually, first, we need to copy all of the contract code because we're going to use Hardhat to compile it in order to make an ABI that we can use to interact with the contract. So let me go ahead and open up the terminal. I'll do npx hardhat compile. And then we will see here the ABI will be added to the artifacts directory. So one quick note though first about the package.json. In this script and all the other future videos when we write our attack scripts, I'm going to be using the regular version of Ethers as opposed to the Hardhat version of Ethers. And then I also will be making for each one some scripts that can be run. They'll save us a few keystrokes in case we need to call the attack script or call a test script multiple times. If you want a copy of this code, of course, as usual, it's going to be down below in the description, linked to the GitHub repo that is. But let's get back to writing our attack script here. So I already imported the regular version of Ethers here. Let me actually remove that just so you can see the difference. So if I were to do this, where I'm creating our provider so that we can have a reference to the node on the blockchain we're trying to use, then when I type the Ethers for autocomplete here, there'll be two options: the Hardhat Ethers and then the standard Ethers. So I'm going to choose this one, the standard Ethers. So let me finish this statement here. So I'll do Ethers. Actually, it should be new Ethers provider. And then, like I mentioned earlier, I'm using Polygon Mumbai. So I'm going to go ahead and paste in that URL. I already have it in my Hardhat config file. By the way, this config here is just allowing us to fork a copy of the Mumbai testnet in case we want to run our tests that way. But we won't be doing that in this video, actually. But nonetheless, I'm just going to copy this from here. Then let me go back and paste that in here. Okay, so now we have a reference to a node on the Polygon Mumbai network. Now we can go ahead and make a reference to our wallet. And basically our wallet is going to be the player address. So we're going to need an instance address. Let's look at that now. I can show you what I mean. So open up the terminals and we'll see we have a player address, which is the same as our wallet address, the one we're going to make a reference to in a moment. So this should be ending in the same characters, 10A20 or 09. Same thing here, 10A09. So the wallet address is the player address. We already have an instance address here. Just to play it safe, we could also create a new one here, but maybe I'll hold off on that. If I encounter some problems later, I might get a new instance, but for now, let's try the one they provided here by default. It has happened, though, where I try submitting an instance, and then it doesn't work, and I get a new instance, and it works. So I'm assuming that's because some other player came along and just, completed the level or did something to make that contract not function the way it usually does. But in any case, let me just try this one first. So going back to our code, oops, wrong way. We'll paste that in here. And now let's make that reference to our wallet. So we'll do ethers.wallet. And then in order to create a reference to our wallet, we need to pass in the secret key, or private key of the wallet. So that's why I'm using the .m, because I obviously want to conceal that. So I called the variable Metamask key. In case you're not familiar with process.m, or .m that is, it's just a npm package that allows you to create a .env file where you can keep all your secret keys and conceal them here so you don't actually accidentally put them on GitHub or something. You want to put this in your git ignore so it doesn't get published accidentally. And that way you can just have this required statement and then make a reference to all your secret keys that way without exposing them. So I have to do that here as well. Make it process.env. Okay, second thing I'm going to pass into this constructor though is the provider. So that way, whenever the wallet makes a function call, it's going to be calling the same blockchain or the same node that we're made a reference to here, which is Polygon Mumbai node. Okay, so now lastly, for the objects we're going to need, we're going to make a reference to the fallback contract itself. So this is going to take 3 parameters. First one is going to be the fallback address, then the ABI, and this one quick thing, notice how it has .abi at the end. That's because the JSON ABI file that Hardhat makes actually includes the ABI itself as a nested object within that object. So that's why it's type ABI when you're importing the file. So in any case, the next thing we're going to do lastly is pass in the wallet. So whenever we're calling the contract, it's going to be on behalf of our wallet. So first thing in the sequence here is we need to call that contribute method. So I'm going to make an object that's going to hold a reference to the transaction when we call that contract method. So here we go. And then the method itself takes no parameters. If you see here, there's nothing here, but we need to send some ether to it or some native token to it, right? It's payable. So the way you do that with ethers is by something called overrides. So you just put an object, and then there's several default overrides you can include. So we're going to be overriding the value. And we'll do ethers.parse units. And we're sending just one way. It's really just a number 1, but nonetheless, I do it this way just because it's more readable. So just 1 and then away. And then if we did have parameters, they would always go before the override. So we had some param, whatever, we put that here. And then lastly would always go the overrides. We're actually going to override a couple more things as well. We're going to override the gas price and gas limit, because sometimes when using ethers, it can't estimate the gas properly, and then it throws an error and reverses a transaction. And because this is a test network, we don't really care about sending, overpaying for gas, whatever. We can just put some arbitrary high values just to avoid running into a gas estimation error. If this was a real transaction we were doing, we would want to use some sort of blockchain scanner and some other means of properly estimating the gas. But here we don't have to worry about that. So I'm just going to put gas price. Let's make it 3 gwei. That's actually not a lot if this were mainnet, but because it's testnet, I think 3 gwei is actually probably a priority price. And then here we're going to put a really high limit of gas, though. We're going to put like 2 million or something. So let's put here 2 million. Okay. So now we need to wait for that transaction to be mined. Actually, we need to await calling the function as well to get the reference to that transaction. And that's the little bit of downside with this approach is we have to await every single transaction to be mined before we can go to the next step. If we could make a smart contract and have all of our code in that smart contract, it could all be wrapped inside a single transaction. However, when I tried that approach, Ethernaut was rejecting it because of, I guess my theory is that it was looking and trying to make sure that the actual wallet address was the owner of the fallback contract and not some arbitrary contract address. So that's why I'm trying this approach, and hopefully this way is going to work. We'll find that out later. Moving on, the next step is going to be sending that small amount of native token to the contract by virtue of a low-level call so that it will trigger that receive function. So we're just going to call send transaction on the wallet instance. And once again, everything has to be await here if we want to do it in sequence. So await send transaction. Then here we're just going to fill out a to property to make that the fallback address. And then after that, everything will be the same as the previous call. We want to override the gas price and gas limit as well as send one way. Then again, we have to wait for the transaction to be mined. And then we have to make one more call to withdraw the contract funds. At this point, we should be the owner, or the wallet should be the owner of the contract. So the next step will be just calling that function, the withdrawals of funds. Actually, I forgot to reassign the transaction object, so we're going to make a group of this transaction now, then await that one. And then now we're going to call the withdrawal function on the contract. Once again, no parameters. We'll go back to the contract just to make sure. So withdrawal, yeah, it's just automatically making sure it's the owner and then sending the balance to the owner of the contract. And then once again, lastly, we have to await that transaction to be mined. Okay, so I think that concludes it here. I almost forgot one more await statement. But yeah, after we run that script, we should be the owner of the contract, and all the funds should be withdrawn back to our wallet address. So let's go ahead and give it a try. And this might take a few moments because we have to wait for 3 separate transactions to be mined one after the other. So even though the block speed is, I don't know, somewhere around 10 seconds probably, nonetheless it could take even more than half a minute just due to the fact we have 3 different transactions to wait for. So if it does take a long time, I'll go ahead and pause the video here and then start it up afterwards, but let's see what happens. Oh, that was not too bad. Okay. So it looks like it succeeded. There was no transaction revert errors popping up in the console, so that's a good sign. Next, I went ahead and made some unit tests ahead of time. So here they are. Basically, we're just going to verify the contract owner is the same as the player address. In other words, our wallet address. And we're also going to verify the contract address has no balance. Actually, we don't need this here. And no need to declare this twice. Not sure why I did that. Let me just move this outside these functions and then get rid of this one. Okay. Now let's go ahead and run our tests to make sure the conditions were met. Oops. So what went wrong here? Yeah, so we do need the fallback address. So let me just copy that over from the other file here. So whenever you get an ENS error, that usually means the address is not valid for whatever contract you're trying to call a method on. And in my case, the address is not only not valid, it's empty, so that would explain that. So now let's try this one more time. Okay, so they both passed. So fingers crossed, going back to the Ethernaut page, let's see if it'll let us submit this instance and if it will pass. Alright, suspensefully waiting for that transaction to be mined here. And it passed. Alright, thanks for watching and see you in the next one.